Solve a system of equations using the substitution method. So we've already learned how to solve a system of equations by graphing, but now I want to do it using the substitution method. But before I do, I'm going to actually graph this for you just so we can see the solution and compare the two. So this function right here, this linear function, is in slope-intercept form, and it's easy to graph, and we know this now. We can start at -3. We could go down 2 and 1 to the right, or we can go up 2 and 1 to the left, as long as we have this negative slope. And then we go up 2 again, and 1 to the left, up 2, 1 to the left. And so we have this line that represents all the equations, all the solutions to this equation right here. The other graph, this one here, is not in slope-intercept form, so we'd have to kind of come off to the side and rework this, get it into slope-intercept form, move the x to the other side. So we have 3y equals -x plus 6. Divide everything by 3, and that gives us y equals -1/3 x plus 2. And now it's in slope-intercept form, and I can easily graph it. Start at 2. I could go down 1 and 3 to the right, or I could go up 1 and 3 to the left. And so it looks like this. And you can see that that's a graph of all the solutions to this function. And where they intersect, which right here is -3, 3, is a shared solution. So that's a solution to both of these. And that's the answer to the system of equations. And that's what we're looking for. But we did this graphically or geometrically. And I'd like to do it algebraically using the substitution method, so a completely different method. So this works nicely when you get whole number answers because you can see it in the graph. But if these were fractional answers at all, you wouldn't be able to tell from the graph exactly what that fraction is where they intersect. So this is a nice method, but it doesn't always work. So we have this substitution method. So here we go. The substitution method is literally when you plug one function into the other function. So this here says that y is equal to -2x minus 3. So it's telling me what y is equal to. So in this function, I'm going to rewrite it, but instead of calling this y, I'm going to substitute in what y is equal to, which is -2x minus 3. So here I go. I'm going to write this function, 3y plus x equals 6. 3y plus x equals 6. But instead of calling this y, I'm going to call it what y is equal to, which is -2x. Let me do that in another color. -2x minus 3. So I'm substituting this into this y right here. And that's called the substitution method, plugging one function into another. And then I just work it out. I just distribute. Notice all I have is x's here, no more y's. So I'll be solving for x. So I multiply this out. That's -6x minus 9 plus x equals 6. Combine these like terms here, -6x and 1x is -5x. And minus 9 equals 6. Add 9 to both sides. -5x equals 15. Divided by -5. And I get x equals -3. That's the x coordinate of my solution. We know the answer from this graph is -3, 3. So there's my x equals -3 right there. So I know the answer is -3 something. If I want to get the y value, all I have to do is plug back into this function here that says y is equal to, and that's what I want to know. What is y equal? If x is -3, I can plug it in here. -3 times -2 is 6, and 6 minus 3 is 3. So once I have one of the variables, one of the x or the y, I can plug it back into one of the functions and find the other variable. Okay, and that's the substitution method, plugging one function into another function and solving it. And it's nice when it's written this way, y equals, so I know exactly, or it could even be x equals, which I'll do in the next example. It doesn't matter which variable you solve for. You could get x first and then y, or you could get y first and then x. So I'll do one more example just to show you that. Okay. So let's look at 2y plus 3x equals negative 4. And the other equation is going to be x equals 12 minus 4y. Now notice in this one it says x equals instead of y equals. It doesn't matter which variable you plug into which function. So in this case, because it's telling me what x equals, I'm going to substitute this in for this x right here. So I'll rewrite this equation, 2y plus 3x equals negative 4. So I'm copying this one, and instead of x, I'm plugging in what x is equal to, which in this case is 12 minus 4y. So I substituted this equation into this equation for the x. Notice all I have is y's now, so when I get the answer, I'm going to have the y value of my answer. So this is 2y, I'm going to distribute here, plus 36 minus 12y equals negative 4. Combine these two like terms, which gives me negative 10y plus 36 equals negative 4. Subtract 36 from both sides. Negative 10y equals negative 40 divided by negative 10. And I get y equals 4. So in this time I solved for y. In the last problem I solved and I got x equals. This time I got y equals. So my final answer looks like this. Something 4. That's the y value. If I want to know what the x value is, I come back over here and I say I want to know what x equals. Well, I know this y is 4. 4 times 4 is 16. 12 minus 16 is negative 4. And this is the solution to this system of equations, meaning that this solution works here and it works here. It makes this equal negative 4. Okay? So this has infinitely many solutions. This has infinitely many solutions. This is the only solution that they have in common. And so this is the answer to the system of equations using the substitution method.